Okay, thank you very much for being here. I've already thanked the organizers. So, again, this is a talk about some theory that is related to a type of non-reversible Markov chain or Markov process Monte Carlo algorithm. And basically, the main aim of the talk is to show you that for some non-reversible algorithms that are that have been of interest, basically one can extend some very simple ordering criteria that have been developed for the reversible scenario to this class of non-reversible processes. Right, so that's so no new algorithm basically. Okay, we are going to just focus on some of the properties. Right, so that's the talk. So I'm going to spend quite a bit of time on the reversible scenario, right? Because once we've covered this Q detail balance, which I talked about last week, and Arno referred to it as well last week. Basically, you will be in a position to guess what the results are going to be. Maybe what is interesting, the things that are perhaps more interesting are the applications. And if time permits, I will move on to the continuous time scenario, but basically the ideas are more or less the same. And I may just tell you what the results look like without providing too many details. Right? So this slide looks very much like my first slide last week. So again, a bit of notation. We are interested in sampling from pi. There are many reasons why we may want to do this. And I'm going to focus primarily on Markov chain Monte Carlo methods. And I think that everybody in the room here is familiar with Markov chain Monte Carlo methods. And this is the sort of questions you may ask about a Markov chain and its use. So last week, I focused basically on the first bullet point here, right? What can you say about the convergence to equilibrium? This week, I'm going to focus on this bit. And in particular, I'm going to be interested in characterizing the asymptotic variance or the variance of these quantities for various algorithms. And in particular, what I'm going to be interested in is this. This is an important fact. So basically, if you want to achieve this, run Markov chains that leave pi invariant, basically the choice is not unique. And you've got to make choices. And there are many things to take into account. There's on the one hand efficiency. So for example, you may wonder, you want to minimize the variance of this estimator for finite n, ideally. Whether you can do it or not is a different thing. And of course, some Markov chains may be more expensive than others. So I will not talk about the cost at all. I will just focus on the pure statistical efficiency of the Markov chains and try to compare various algorithms and show you that there are very simple criteria one can use. Right? So this is the motivation for the whole talk. So we want to ideally guide the design of algorithms. And now I'm going to switch a bit to reversibility. So reversibility plays a central role among existing algorithms. Basically, at least the building blocks of standard Markov chain Monte Carlo methods are reversible. And one bonus that comes with reversibility is that there are many theoretical results, and I will review some of them. So that's a very nice thing for people interested in the theory. But in practice, this is not necessarily a desirable property. To start with, it is a constraint, right? So you may be interested in trying to lift this constraint and basically explore a bigger set of algorithms, okay? But also there is that problem in some standard scenario that basically you end up with a random walk behavior, which may not be a good idea, right? So there's been renewed interest, and I think that there were at least two talks last week on these ideas. And what I'm going to show you is that some of the results that exist for the reversible scenario work also both in the continuous and discrete time scenarios for a particular class of non-reversible processes, right? So that's the idea. And basically, well, maybe I'll quote one result which is slightly orthogonal to the rest of the story, but it's nevertheless interesting, right? So I will start again with the Metropolis Hastings algorithm, and I think I'll go through it extremely quickly. So we all know about the random walk Metropolis in this room. The only important thing in this transparency is R, okay, the acceptance ratio, because I will refer to this quantity, so just try to remember this piece of notation, right? So the detail balance condition, well, the Metropolis Hastings algorithm is not very difficult to show that basically it satisfies this type of property, right? So that's detail balance, which of course is nice because we can, well, the Metropolis Hastings algorithm satisfies this property, and this of course ensures that pi is left invariant. So what about the term reversibility? And the only reason I mention this here is that I will at some point refer to that notion of reverting time. Okay, so what is reversibility? Basically, if you consider a process that satisfies this property at equilibrium, basically if you change the arrow of time, negate time, basically the law of the process remains invariant, right? So it's the same law, right? So that's just a repeat of what I said. It's nice theoretically, but in practice it may not be a good property if performance, whatever it is what you're interested in. Okay, so I'm going to reintroduce a bit of notation that I used last week, and really the notation is here to make things simpler, believe it or not. Okay, and basically the notation is very much related to the notation that Pierre introduced last week, and basically you can replace some of the letters with vectors and matrices if that helps. Okay, so first thing, we are interested in sampling from pi, but in many situations, as I mentioned last week, basically it may be a good idea to sample from another distribution mu, right, from which is such that if you can sample from mu, you can recover sample from pi, right? So it's the same idea as what I explained last week. I'm going to think, so P was the transition probability of the Metropolis Hastings algorithm, or here in general of our Markov chain Monte Carlo methods, and I'm going to use this notation to mean this. Okay, so that's the conditional expectation of f with respect to your transition probability, given that you've started at x. And again, you can think of f as a vector and p as a matrix, and you would use the same notation in that case. Right? I'm going to consider the functions that are square integrables with respect to the distribution we are going to try to sample from. These are the centered functions. And importantly, I'm going to use an inner product. Okay, so if f and g were vectors, you can imagine that you would say, oh, it's f transpose g. Well, you can generalize this idea to matrices and weight the matrices, the vectors. Okay, so think of this as a dot product between f and g, right, weighted by the invariant distribution you're interested in. Right, and I'm going to use, in some places, the associated norm. Right, so what is important here is that instead of talking about detail balance, I'm going to talk about a joint operator. So what is the idea of an adjoint? Well, you can think of it as being a generalization of the transpose of a matrix. That's one way to think about it, except that here we are using a strange inner product, so you've got to generalize the idea. But the analogy with matrices works, because what it says is that the adjoint of P, which we call P star is such that for any f and g, fpg, so pg is this, should be equal to P star Fg. So basically what it means is when you apply the transpose to a product of a matrix and X, you get X transpose A transpose. It's the same idea here, right? And that's it. So this makes the presentation much simpler because there is one property which is called self-adjointness. So assume that somehow your matrix is symmetric, right? This is what you would get, okay? If you change, if P moves here, basically you've got the equality. So basically what we are saying here is that the adjoint of P is itself, self-adjoint, right? And it's not very difficult to show that this is equivalent to detail balance, right? So basically, instead of talking about detail balance, I'm going to use about this property. And why is it important? Because I'm going to focus on the adjoint, all right? So as soon as you're not reversible, basically P star is not equal to P, but may take a form that involves P, and that's what I'm going to focus on, okay? So this is a very strong property, and that's why there are many theoretical results. So for example, there's a spectral theory. You can diagonalize symmetric matrices. Well, you can, in some sense, diagonalize self-adjoint operators, and that leads to many very nice results. This is one, an example. A nice fact, though, is that in this scenario, there is a nice way of comparing performance of reversible Markov chain, which share the same invariant distribution, right? So you see, we are getting back to the initial question that I was asking. I want to sample from mu, and I've got to choose between P1 and P2, two transition probability. Which one should I choose, right? So I'm going to ignore the cost here. And I'm going to focus primarily on this quantity, which I will refer to as the asymptotic variance. So basically, that's so here you've got the variance of your estimators of the expectation of f with respect to pi or mu, and you look at the variance, you rescale by time, and you look at what happens when t goes to infinity. And of course, what you want to do in practice is to minimize this quantity, right? You want the smallest variance, because roughly speaking, what you're saying is that the variance of what you're interested in is going to be this quantity divided by t, right? So that's the constant you're interested in, right? So an example of...
P star is a probability.
Pardon?
P star is a... Sorry, it might be a dumb question.
It might be. It might be.
P star is that's my get out of jail card.
Yeah.
P star probability.
So when P equals P star, yes.
But otherwise,
it probably...
Because mu P is a measure.
Uh-huh.
So
Yeah.
And it's equals to with the version of P star on cylindrical sets.
Uh-huh.
P star is the backward kernel.
Is the backward kernel, okay? So it's basically you can... mu P divided by mu. Yeah. Yeah. So let's go back to the Metropolis Hastings algorithm. In fact, Metropolis, so we all know this. Basically, with Metropolis, we take the mean 1 and the acceptance ratio. But it turns out that there is another choice that is possible. If you choose, instead of mean 1x as a function, you choose x over 1 plus x. Basically, this the algorithm that would use this alpha would still be valid. And in fact, you would still satisfy detail balance, or the operator, which would still be self-adjoint. So a natural question, which was solved a long time ago, is what is the best choice? And of course, this is the best choice, right? So we'll see why in a moment. Okay, so that's, a very silly question to illustrate a more general point. Okay, so there's a general result that can help us answer this question and many other questions, which is Peskin's result. right? So here we've got two Markov transition probability, which are assumed to be reversible with respect to a common distribution mu. And this is what the theorem says. So the theorem says two things. It says that if you can compare the transition probabilities in this way, that is for any x and any measurable set, you've got this inequality. So it's the probability somehow of leaving any state, okay, because x is not in A. So the probability of leaving any state for one of the two kernels is assumed to be larger than for the other one. Then what you can deduce is, well, something that is somewhat intuitive. You can deduce that the variance of the chain that moves faster around, basically, is going to be smaller than the variance for the algorithm, which is a bit slower. That tends to be a bit sticky, basically, right? So that's basically one thing. The other thing. So this is starting from mu. That's at equilibrium, okay? So that's the thing. For those of you who know about these things, in fact, the theorem also tells us something about the right spectral gap, right? And basically, the right spectral gaps are also ordered the way you expect. So basically, in many scenarios, this will mean that pi 1 also converges to equilibrium faster than pi 2. Not always, right? But for most chains that you design in practice, this is going to be all right. So this is very interesting, and one advantage of this theorem is that it is applicable, right? In many scenarios, you can get a handle on this, right? So that makes it very useful. So for example, you remember the competition between Metropolis and Barker. You remember that the only thing that we did was to change the acceptance ratio, right? But there is this inequality, right, which tells us that basically when you propose you're at x, you propose a z to move to y. Basically, this the probability of accepting this transition with a Metropolis algorithm is going to be always larger, right? So you satisfy this criteria. And in fact, it can even be shown that this is the optimal choice, right? But that's a separate thing with some additional is the optimal choice. Okay, so in fact, this result is basically implied by something that is more general, right? And so we are moving closer to the things I'm interested in. So in order to present the more general result, which implies Peskin's result, we need to introduce the Dirichlet form, right? So the Dirichlet form is the inner product between F, so this is the identity matrix or the identity operator, minus your transition probability times F. And if you don't like this, you can think of this quantity as being the variance. So if F is centered, right? So if F is centered at mu, that is, it has expectation 0 with respect to F. This is the variance of your function minus the first autocorrelation term of the Markov chain at equilibrium. Okay, so that's the interpretation. So basically, I'm going to order the Dirichlet forms. If you don't like Dirichlet forms, just think that you're trying to order the first order autocovariance term of the Markov chains at equilibrium. And what the general result says, it says that if for any function that is square integrable, you can order the Dirichlet forms in this way, right? Then basically it is a good thing for pi 1. So its variance is smaller and the right spectral gap is larger. Okay? And basically in some scenarios you can basically the Peskin result cannot be used, but you can use this result. And it is helpful. And it's not very difficult to show that this implies Peskin's result. Okay? So here it's only from mu. I don't know beyond.
If you look at the evolution of the first, second moment,
Yeah, but to do what? This is what I don't understand. So
Probably some comparison between the variance, not starting from, it might be possible.
or do you mean for two Markov chains that do not share the same invariant distribution?
Oh, they start from two different.
From two, so here, in here, that's your problem.
Starting
From this. So I guess it's possible because of what I was telling you, it's a similar problem, except that the only results I know are for the scenario where the state space is discrete and finite. And then you can work with the Dirichlet forms, and there are additional coefficients in front of the Dirichlet forms, okay, that you add. So basically it's the Radon-Nikodym derivative that you bound somehow to take into account the fact that you're not. So I'm not sure it really answers your questions, but that's the sort of thing that exists in the literature.
So is mu invariant in the pi?
Yes, yeah. So here it's whatever you want. Okay, here certainly pi 1 and pi 2 leave mu invariant. Okay, right? So, so there are many applications of these results, and basically it's settled at some point once for all the question of which acceptance ratio you should use. So there's no need to talk about it except as an example. Okay, and there are more exciting applications of this. Okay, but recently there's been an interest in a type of Markov processes for the purpose of Monte Carlo that are non-reversible. But in fact, they are non-reversible in a way that looks like reversibility. And you can take advantage of that. And what I will show you is that one can extend a Tierney result, partially at least. That is, basically, you can order the asymptotic variances with a criterion that looks similar to the Dirichlet form criterion, but there's a twist, right? But the spectral gap or the radius of the operators, we don't know, and I think it's not the case that you can order things just with the Dirichlet forms, right? So we will partially extend this result, right? So I'm going to move to the modified detailed balance. So this is, again, an algorithm that I talked about last week. So the random walk metropolis on Z, right? And this is a random walk. So we choose a ±1 increment with probability a half, and this is the acceptance ratio, and that's potential problem at equilibrium. Gustafson's walk, random walk, looks like this. And again, it's just a repeat of what I said last week. So we extend the state space, and we are going to sample from this distribution now. And we cover samples from pi, if we can sample from the joint distribution. And the algorithm looks very much like the metropolis algorithm, except that now we are sampling on the joint space of x and the velocity or the increments. The acceptance ratio is the same, right? And basically you move to x plus v with the metropolis Hastings probability, and otherwise, basically you reject the move on the x component, but you flip the sign of v, right? So I explained that last week. So in other words, what happens is that the process travels in the same direction until a rejection occurs. Okay, so you get straight lines. Right, so in this scenario, basically the algorithm doesn't satisfy detailed balance, but it satisfies this property, where basically you see, in order to satisfy detailed balance, basically you would need a plus and a plus here, right? And that's not the case. So we don't satisfy detailed balance, but this is not far from detailed balance. So now I'm going to try to move back to the operator setup, because that makes things simpler. So let's try to see what this means in terms of operators. On V, yeah.
So it's the same. I mean,
What do you mean? Is this?
by the W or minus.
Oh, yeah, so there are many other ways you can write this identity. You could put a minus here and not here and things like that. Okay? Yeah, I could put a minus W here if I wanted. It's the same as without the... Yeah, but I've got the pluses on the left-hand side. You know, when I change some of these signs, I've got to change them in everywhere. Yeah, but you're right that here, for example, I could put minus W. Right? Okay. So in order to rephrase it in the operator setup, I'm going to introduce this operator. Okay, so an operator Q, which is going to act on functions. And basically what it does is I give you a function at xv, and you just flip the sign of v. Right? And what is important is that you can rewrite this in this way. Right? So basically, the skew detail balance, you can think of it in this way. Right? So basically, what we are saying here, if you think about the operator setup, what we are saying is that the adjoint of P is QPQ, where Q is a simple operator. Right? And here, the simple operator is just flip the sign of V. In fact, basically, Q is not unique. Right? So there are more operators that are interesting. So you can talk about isometric involution. So that's basically intimidating word just to say this. So basically, what we are interested in, and basically our results will hold under these conditions. So basically what you're saying is that the inner product for F and G is the same as the inner product for QF and QG. Right? And obviously, it's going to work in our setup when Q is the sign flip operators because of the symmetry on the V component. And it's an involution. So basically, when you apply it twice, basically, you get the identity. Right? So you can ignore this comment here. What I'm going to tell you, and I'll show you an example that I will try to detail, is basically the sign flip is not the only possible operator. Okay, and that's interesting. And now that we've got all the ingredients, one can talk about mu Q self-adjoint operators. So what we're going to say is that an operator P, and here a Markov chain transition probability, is Q self-adjoint if basically the adjoint of P is QPQ, where Q satisfies these two properties. Okay? So you see, you're not self-adjoint, but nearly self-adjoint.
Sorry to interrupt. The adjoint is unique usually, no?
Yeah, here, yeah.
So how you can have different Qs, but you get the same operator.
You can have different
The
Q.
adjoint, let's say P star,
Yeah.
can be written as QPQ for many Qs, but it's the same operator. The choice of
That's what you. So for a P, it's so I haven't looked at that, but it's probably unique. The Q, yeah, it must be.
No, maybe there are many, but the QPQ is unique. But QPQ is P star.
Mm-hmm.
P star is unique.
Uh-huh.
There are many Qs. It can be written in many ways. It seems.
Yeah, I'm not sure. I would have to write things in detail, but I don't think it's. I think it's.
P star is unique or not?
P star is unique. Yeah. For
You find one, which is QPQ.
yeah.
And there are many ways of writing, and this is P star. So there are many Qs such that P star is QPQ.
No. I think the Q is unique. If I give you P, the Q is going to be unique. Okay, I would have to prove it, but It's not going to be...
Not clear in many dimensions.
Okay. Because there are quite a few constraints on Q. Okay? Right. So this is what we are going to deal with. So we've generalized things a bit. But anyway, what I was interested in is I've got a process and I want its adjoint to be of that form. And I'm not interested in the, I was not interested in the unicity or not. Mm-hmm. Right. So just one fact, because I will refer to this at some point. Basically, it's not difficult to check that basically QP or PQ are self-adjoint, right? And another point is that basically because of the involution, you can always say that P is QP or PQQ, right? So I just said that this is self-adjoint, this is self-adjoint, and Q, in fact, you can check, it's not very difficult, it is also self-adjoint. So basically, we are dealing with Markov transition probabilities, which are the composition of two reversible chains that leave pi invariant. Okay, but of course, the composition is not necessarily, and one of them has got a special, very special, particular property. But of course, the composition of two reversible kernels is not necessarily reversible. Right, so there's some structure here. So here, just a slide to show you, and hopefully I'll have time to go through the application, the detailed application of this. There are more specific, more practical application of what I'm going to say, but you need another hour to explain what you're doing. So here is a simple example where Q is not a sign flip. Okay, so what is it what is the idea? So it looks completely artificial, but it has one theoretical application. So we are going to consider a bivariate Markov chain. So here what I've illustrated is a transition probability for a bivariate Markov chain, which is built as follows. So there are two components, and I'm interested in sampling from the distribution pi times pi, right? So just the product. And I'm going to use two transitions on the subspaces that I'm going to apply to each of the two components. And P1 and P2 are going to be assumed to be pi reversible. So they are reversible with respect to pi. And this is how the chain works. So basically, the first component uses P1 and sends it to Y2. And then the second component uses P2 and sends it to Y1, right? So why is this of potential interest? Well, if you think about what, okay, so when you go up, you use P1, P2, P1, P2. So I'm just following one of the two paths. So you see that basically this is a non-homogeneous chain. If you just look at this chain, right? But here, by using this trick, what you manage to do is to embed it into a time homogeneous Markov chain, right? So it might be that if you can use some time homogeneous theory to deduce something, right? It may be that because of the independence, you see, the two chains are completely independent. The one that starts going down, up, they are completely independent. So it might be that you can use the time homogeneous resource to deduce something about a particular type of time non-homogeneous Markov chains, right? So what is the link with the Q-self-adjointness? So basically here, just assume that you reverse time, right? Because the notion of adjoint is linked to what happens when you reverse time for your process. So that's why I considered reverse time. So now what you see is because P1 and P2 are assumed to be reversible, if you reverse time, you still use P1 and P2, right? But here what happens is that you see the component that is at the bottom basically now uses P1, right? And vice versa. Okay. And so you see that basically the adjoint, so basically here we've got P star. But you see that P star is different because now we flipped the components here. So basically what this says is that in order to establish that the adjoint is of this form, what I've got to do is to introduce the operator that flips the components. You see, this is what you've done. You've said, when I look at the process coming back from the future, it is as if I had swapped x1 and x2, right? So we didn't swap time, we swapped the components, right? And now, if you believe me, and I'll try to explain a bit of that later on, because in fact we've embedded two not time in homogeneous Markov chain in an homogeneous Markov chain that has got this property and for which we can in general prove something. You can deduce something about some time in homogeneous Markov chains, right? So it's not straightforward yet, but you can imagine that somehow there's a link between the asymptotic variance of these two subchains for a particular function and the asymptotic variance of the bivariate chain. That's somehow the trick. There are other applications in physics of this idea, but that's the point here is you can go beyond the flip assign. Okay. So now how do we extend the results that are valid for Markov? So I'm not going to talk about this, actually. No, I'm going to talk about this, sorry. So remember, we're interested in when it exists, okay, and when you can and when you can write things in this way. So for example, if your Markov chain is geometrically convergent and things like that, all this makes sense. I'm interested in these quantities. So this lambda here is just here to make sure that the thing I'm talking about exists, right? And lambda is still is less than 1. And basically what you're really interested in is the limit when it exists and when lambda goes to 1. Okay, so basically this is a partial result in practice because you've got to sort out what happens when you go to the limit, right? And I'm not dealing with that. That's not interesting. Okay, and it's hard. Okay, so what does the result say? So you remember the TNE result says, just order the Dirichlet forms of P1 and P2. If you can do it for any L2 functions, then you can deduce something about the asymptotic variance and the right spectral gap. So here the result is perhaps not surprising. Basically what you're going to do is order Dirichlet forms, right? But you see what you've got to order, you're not ordering the Dirichlet forms of P1 and P2, but the Dirichlet forms of the symmetric parts of your transition probabilities, right? So you remember I said, you can think of P as being QQP or PQQ, right? Basically, and I told you QP or PQ are reversible. And these are the Dirichlet forms that you're going to order. So that's perhaps the only surprising thing in this result, okay? And what is nice is that you can check that in practice on many examples, right? So one thing that I'd like to draw your attention to is that basically we can order the asymptotic variances. So there's that lambda that's purely technical, okay? You're not interested, but what is important is that we are not ordering for any function. Okay, we are ordering for functions that are left invariant by Q. Okay, so if you think of the sign flip, basically what we are saying is, if you consider a function of x only, basically it is in this class of functions. And at the end of the day, that's what we are interested in, right? Okay, so the result is extremely simple and transparent. So I'm not going to go through the proof, but it's very similar to the sort of things you can do on operators for the reversible scenario, but you use the additional properties that were there. So the Q self-adjointness and the fact that the function is left invariant by Q, right? Okay, so now a bit more about the link with basically inhomogeneous chains. Because in fact, you can prove the result that I've talked about using a result that has been established for inhomogeneous chains by these people. So Mayer, Duke, and Olsen in 2014. And somehow there is equivalence between the two results, which I think is interesting, but there's something interesting with the Q self-adjointness. Right? So in this paper, what the people who were looking at this were doing, they were interested in basically studying this kind of processes. Okay, so you alternate between P1 and P2. They are both invariant with respect to some common invariant measure, and they are reversible. I can't remember if I said that. And what they were interested in saying is, let's imagine that I've got two ways of doing this. Okay, so here this is a 2, 1, 1, and let's imagine that I've got another way of doing this, which I call way 2, but for recipe number 2, I've got a first kernel, and I've got a second kernel. Okay, and here I do P2, 2. Okay, so they should be in sync here. So the question they ask can I extend Tierney's results, right, if I know how to order the P21 and P11, okay, and the P22, is it P22 and P12, right? If I can order the Dirichlet forms pairwise like this, right, can I deduce an ordering of the asymptotic variances? And that's what they proved, right? So that's exactly what they proved. So of course there was a 50% chance that I would get it wrong. So you've got to flip these two indices here, okay, for the notation to match the theorem. But what the result says is that basically if you can order the, no, that's correct. I chose the right way. If you can order the Dirichlet forms pairwise for any square integrable function, right, then for some functions, actually, which have got the property in disguise that QF should be equal to F, okay, you can order the asymptotic variances, okay. So that's the detailed version, and I'm not going to dwell into this, but what is important is that in the light of what I told you earlier, basically a Q self-adjoint operator can be thought of as being the composition of two reversible kernels that leave mu invariant, right? So you apply this result, and basically you get our results automatically, right? But because of this construction, you can also prove their results from our result. So they are strictly equivalent up to some technical details, but that's the same idea in disguise, right? Okay, so I won't go into the details of the proof, but
why stop at 2?
it doesn't work. I've tried, okay? It doesn't work. And I think that someone told me that they had a counterexample, but I can't remember who.
So basically, you've got 3 kernels that I want to run in succession, and I know they're better than 3 other recipes. I shouldn't do this.
Well, we don't know.
Okay.
We don't know. Yeah. Okay, and here I'm just mentioning some applications. So for example, one silly application is, we've got the Gustafson algorithm that looks like the Metropolis Hastings algorithm. So of course I could choose the Barker dynamic acceptance probability. And you could ask the question, is it the same, is the result the same as for the reversible scenario? Is it always better to use this, right? Where at least when it comes to asymptotic variance, what our result says, and you can do the calculation. So you compute the Dirichlet form, you polarize and everything. What you can show is that basically using this is always better in terms of asymptotic variance, thanks to our result, because you can order the Dirichlet forms. Okay, so there are quite a few applications, and basically there were some conjectures in physics, for example, from the authors of this paper. And basically for all these algorithms, basically with one small bit of theory, basically we got a firm answer about what happens to the asymptotic variance. Okay, we don't know much about the convergence to equilibrium, and the two things may contradict each other in practice. Okay, so basically what I'm saying here is don't always follow what the theorem tells you. Okay, because you may have some surprises when it comes to when you look at the asymptotic at the convergence to equilibrium. Okay, and there are very simple examples where you can see that. Okay, so yeah, well, so really that's just to relax a bit. Just a result that has nothing to do with our other results, but I think it's interesting to point out that it's not very difficult to show, and really that's related to standard results. So if you consider the guided walk, so here what we've just did is we've ordered Q-self-adjoint processes, right? We can actually even order non-homogeneous chains that consist of cycles of length 2 of Q-self-adjoint operators. Okay, so I haven't detailed this, but that's also possible. But here the question we are asking, and it is not a very silly application. So what about the guided walk versus the random walk metropolis algorithm? Which one is best if we can order them? In terms of asymptotic variance, you can. So for those of you who know about these things, basically here I'm considering the symmetric part of the guided walk, right? But when you think about it, the symmetric part of the guided walk, which is this, just says at each iteration, right, instead of using the v from the previous iteration, just choose at random between plus v or minus v. And then you apply the acceptance ratio. But the acceptance ratio was the same for the guided and the random walk metropolis. So basically this here is the random walk metropolis algorithm, which is the symmetric part of the guided walk. And there is a general result that tells you basically that you've always got this order. Okay, so coming up with expressions for the gap is quite complicated. I mean, there's an expression, but I don't know how to use it, right? So that's an illustration of the fact that sometimes, right, so you see there's a particular structure. We are comparing something that is non-reversible with its symmetric part. And it's not always the case that the symmetric part is a sensible algorithm that we know about, that we care about.
Instead of the average, what about the multiplicative reversibilization, so P times P star?
So that we don't know. We don't know.
You definitely have to lower inequality because 1 is always better than here, P star. But it's just the second inequality.
Yeah, and when you look at product, then you've got to be careful because you can look at averages at each time instance or every 2 time instance, right, when you compare the variances. And so you've got to be clear about what comparison you... Yeah.
You have to order each of the components of the cycle.
Okay, so in that paper of mine that I was citing earlier, basically there is a comparison between the, what is it? If you like, the equivalent of the random scan Gibbs sampler versus the cyclic Gibbs sampler, right? but it's generalized to general reversible chains. And in that case, basically, the cyclic one is always better in terms of asymptotic variance, right, versus the random scan. Okay, so you compare the algorithm where with probability of half you choose P1 or P2, or you cycle between P1 and P2, right? But you look at what happens at each time instant, right? So in that case, you can order the chains, and it actually relies on this result and something that I said earlier. And in that case, basically, what you can show is that the deterministic one always wins in terms of asymptotic variance, right? So what is interesting is that when it comes to convergence to equilibrium, basically there are examples that prove sometimes one is better than the other. So there's no order in terms of convergence to equilibrium. So in scenarios where you can do the calculations, right? So just a quick word about the continuous time, because you can guess how it's going to work if you're familiar with this thing. So I've already talked about the zigzag last week, and I think that we all get the idea. This is the type of process you're looking at. And basically, this is how you generalize, and that's not surprising if you're a bit familiar with this thing. This is how you generalize this idea, but it's much more technical. So here, basically, instead of working with a transition probability, you're going to work with the generator. And Q-self-adjointness in this scenario, basically, is going to be defined in this way. Okay, so you just replace P with the generator, and you introduce lots of technicalities, right? That's to make sure that all these things exist, right? So that's much more complicated, but at least the statement of the result is fairly simple. So this is what we want. So we've got two processes that leave the same distribution invariant, and they are both Q-self-adjoint, right? So in the sense that I described earlier. In the continuous time setup, this is what the Dirichlet form looks like. So it's a function of the generator. And the result is really as you expect it to be. What you do is that you try to order the Dirichlet forms for the generators, but for Q times the generator, right? So if you can do this, and for some nice functions, then basically what you can do is that you can order the asymptotic variances for the continuous time process, right? And that's it. Thank you.
Okay, we had several questions during that, but we can take one or two questions before moving to the second speaker.
So, in MCMC application is sometimes based off really conditioning of the distribution. Do you say, or have you ever seen people using this like comparison argument, trying to understand what's the best choice of preconditioning?
So,
like for example, you have a Gaussian distribution. Let's say.
So you're changing the invariant distribution.
I'm sorry?
You're changing the invariant distribution.
Yeah, no. I mean, you have suppose you want there's a target distribution which is you write it down, and then it's the way you write the proposals, right? And the question is like, which is the best proposal you can obtain? Often like.
Oh, right.
You don't sample directly from isotropic, Gaussian.
Okay.
You don't do something different, right?
So that's a very good question. So with actually with Alain Durmus, we try to look at something really silly. Okay, so there are those asymptotic results, rescaling results that tell you if you consider the random walk metropolis with a Gaussian as a target and a Gaussian as a proposal, basically you should somehow your proposal distribution should have somehow the same covariance matrix as the target up to a scaling factor, right? But this is an asymptotic result. So what we try to do the exact calculations, on the Dirichlet forms and everything, and it doesn't work. So it's not tractable. It's not tractable. It's very hard to deduce anything, and I'm not aware of any exact calculation. There are some asymptotic results that say, yeah, this is how you should do it. But and see, if someone has managed to do it, I'd like to see how they've done it. Yeah.
Do you get any sort of ordering with the PDMP?
Yes. So for the PDMP, so that's a good question. We prepared that before. So basically, so there's one nice thing and one disappointing thing. So basically what the PDMP tells you, so there's the equivalent of, so there are several things. So first, if you look at the zigzag process, what you can do is that you can write the difference between the Dirichlet forms in this way. Okay, so you can, so this is the zigzag, you remember, you wait a certain time and then you choose between various options where you flip the sign of one of the components of V. So you can write the difference of the Dirichlet forms in this way, right? And of course, what is nice is that this suggests that basically, so if the sign is not wrong, okay, this suggests that you should choose your intensity as small as possible. Okay, if you're interested in the asymptotic variance, what you want to do is to make sure that your intensity is as small as possible. Which sort of, you know, if you start using your hands and things like that, means you want less events, right? So less noise in the system. So for the zigzag, this is what it says. And it turns out that there is an equivalence of the mean 1x of Metropolis in this case, which is what people refer to as the canonical choice of the intensity, which leads to the best asymptotic variance, right? Unfortunately, if you look at and maybe I've got it, if you look at the bouncy, things are a bit more complicated. Because in this case, you see, the term between brackets is not necessarily positive or negative. The sign is not necessarily constant, right? So we haven't been able to conclude. It doesn't mean that the result doesn't work, okay? Because basically, when you try to order the Dirichlet forms for all functions, you're asking more than what is actually needed in the theorem. It's just that the functions for which it would be sufficient to order the Dirichlet forms are intractable. You can't use them in practice. So what you do is that you establish the result when you can prove the order for the Dirichlet forms for any functions. So B is the bounce, basically. Is the bounce of the bouncy particle sampler, right? And so it's basically, I've got a bounce that because the choice of the intensity in BPS or zigzag that ensures that you leave mu invariant is not unique, right? You can add 3, okay, to any valid intensity and it still works. It's just that what these results, what we would have liked these results to say is that adding 3 is not a good idea. But in fact, we don't know. It doesn't mean that it's not true.
Okay,
Yep.
I suggest we